School of Management Studies IGNOU presents an audiobook on the course MMPC 005 Quantitative Analysis for Managerial Applications for MBA program. Block 2 Probability and Probability Distributors. Unit 8 Decision Theory.
After completing this unit, you should be able to structure a decision problem involving various alternatives and uncertainties in outcomes, apply marginal analysis for solving decision problems under uncertainty, analyze sequential problems using decision tree approach, appreciate the use of preference theory in decision making under uncertainty, and analyze uncertain situations where probabilities of outcomes are not known. Introduction. In every sphere of our life, we need to take various kinds of decisions. The ubiquity of decision problems, together with the need to make good decisions, have led many people from different time and fields to analyze the decision-making process. A growing body of literature on decision analysis is thus found today. The analysis varies with the nature of the decision problem, so that any classification base for decision problems provides us with the means to segregate the decision analysis literature. A necessary condition for the existence of a decision problem is the presence of alternative ways of action. Each action leads to a consequence through a possible set of outcomes, the information on which might be known or unknown. One of the several ways of classifying decision problems has been based on this knowledge about the information on outcomes. Broadly, two classifications result. Number 1. The information on outcomes are deterministic and are known with certainty. And number 2, the information on outcomes are probabilistic with the probabilities known or unknown. The former may be classified as decision-making under certainty, while the latter is called decision-making under uncertainty. The theory that has resulted from analyzing decision problems in uncertain situations is commonly referred to as decision theory. With our background in the probability theory, we are in a position to undertake a study of decision theory in this unit. The objective of this unit is to study certain methods for solving decision problems under uncertainty. The methods are consequent to certain key issues of such problems. Accordingly, in the next section, we discuss the issues, and in subsequent sections, we present the different methods for resolving them. Students can refer to their self-learning material for learning about the different methods for resolving them. Certain key issues in decision theory. Different issues arise while analyzing decision problems under uncertain conditions of outcomes. Firstly, decisions we take can be viewed either as independent decisions or as decisions figuring in the whole sequence of decisions that are taken over a period of time. Thus, depending on the planning horizon under consideration, as also the nature of decisions, we have either a single-stage decision problem or a sequential decision problem. In real life, the decision maker provides the common thread, and perhaps all his decisions, past, present, and future, can be considered to be sequential. The problem becomes combinatorial and hence difficult to solve. Fortunately, valid assumptions in most of the cases help to reduce the number of stages and make the problem tractable. In the earlier unit, we learned a method of handling a single-stage decision problem. The problem was essentially to find the number of newspaper copies the newspaper man should stock in the face of uncertain demand such that the expected profit is maximized. A critical examination of the method tells us that the calculation becomes tedious as the number of values the demand is taking increases. You may try the method with a discrete distribution of demand where demand can take values from 31 to 50. Obviously, a separate method is called for. We will be presenting marginal analysis for solving such single-stage problems. For sequential decision problems, the decision tree approach is helpful and will be dealt with in the later section. The second issue arises in terms of selecting a criterion for deciding on the mentioned situations. Recall as to how we have used expected profit as a criterion for our decision. In both the marginal analysis and the decision tree approach, we will be using the same criterion. However, this criterion suffers from two problems. Expected profit or expected monetary value, that is EMV as it is more commonly known, does not take into account the decision maker's attitude towards risk. Preference theory provides us with the remedy in this context by enabling us to incorporate risk in the same setup. The other problem with expected monetary value is that it can be applied only when the probabilities of outcomes are known. For problems where the probabilities are unknown, one way out is to assign equal probabilities to the outcomes and then use EMV for decision making. However, this is not always rational, and as we will find, other criteria are available for deciding on such situations. For the purpose of this unit, we will be discussing the issues that we have mentioned so far. This will be achieved through a study of number 1, marginal analysis for single-stage decision problems. Number 2, decision tree approach for sequential decision problems. Number 3, preference theory. And number 4, other approaches for problems where probabilities are unknown. Marginal analysis. We have learned how expected value can be used while deciding on one alternative from among several alternative courses of actions, each of which is characterized by a set of uncertain outcomes. It is easy to see that the computations become tedious as the number of value the random variable can take increases. Decision tree approach. In the earlier section, we have learnt about a single-stage decision problem. Quite often, the decision maker has to take decisions in a sequence, the decisions coming later in the sequence being dependent on those coming earlier. The sequence is either built-in or it is possible to engineer such a sequence for a better decision. For example, consider the periodic production decision for a certain item with uncertain demand. Say refrigerator, for each period, a decision on the number of units to be produced is to be taken given the uncertainties in demand during different periods. Thus, we will have a number of decisions for each period with intervening uncertainties in outcomes for each decision between any two periods. In such cases, the sequence is built in. In contrast to this, we find situations where the time frame of decisions are such that before going for the final decision, it is possible to go for a method for generating extra information that will facilitate the final decision. For example, before deciding on marketing a product nationally, one can decide on test marketing. Similarly, in a production situation where a machine produces an unknown percentage of defectives, one may have an option to buy a special attachment that helps to produce a known low fraction of defectives. The trade-off then is between not buying the attachment and thereby risking a high percentage of defectives and buying the attachment at a cost to safeguard against the risk. An infinite sequence of decisions can be engineered in this case by allowing sampling from the current process to ascertain the percentage of defectives. Thus, at each stage, we can have two alternatives. 1. Buying, and number 2. Not buying and sampling. This can go on till we decide to stop sampling due to some reason. For example, sampling cost becomes prohibitive. The decision tree approach provides us with a useful way to analyze such sequential decision problems. Preference theory. So far, while deciding on an action, we have used the criterion of maximizing the EMV or expected payoff. This does not take into account the decision maker's attitude towards risk. If a company is financially weak, it may decide not to use the EMV maximizing action if there is even a small chance of going bankrupt following that action. Preference theory helps us in such situations by providing a systematic way of measuring the consequences on a preference scale that reflects the decision maker's attitude towards risk. The procedure consists of eliciting information from the decision maker or DM on his certainly equivalence, that is CE, corresponding to each alternative. CE of an alternative being the amount he is ready to exchange for the uncertain consequences of the particular alternative. For example, consider any alternative of investing in a project, the possible outcomes of which are: number 1, net loss of rupees 1 lakh with probability 0.1, and number 2, net gain of rupees 20,000 with probability 0.9. Now, if the DM is risk averse, he might not like even the small odds of losing 1 lakh, and he might be content in having an alternative paying him a certain amount of rupees 5,000 as against the mentioned EMV of above rupees 8,000. You can imagine that this investment gamble is the exclusive right of a class of people and our DM is one among them. Thus, if the exclusive right is allowed to be sold to other people, the DM is ready to sell it for rupees 5,000. The difference between the EMV and the CE is defined as the risk premium. Here CE is rupees 5,000, hence the risk premium is rupees 3,000. As the number of alternatives increase, it becomes difficult to collect preference information in this way. The preference curve, which is a plot of the monetary value on x-axis and the preference on y-axis, is then obtained. First, the best and the worst consequences corresponding to any decision are identified. The preference values of 1 and 0 are then given corresponding to the best and worst consequences respectively, giving us 2 points in the preference curve. Once the preference curve is drawn, the preferences corresponding to each consequence of the problem can be obtained. In the same decision tree, the consequence can now be replaced by the preferences and the criterion of maximizing expected preference be used for arriving at the decision. Other approaches. In the foregoing sections, we have assumed that the probabilities associated with the outcomes are known. In practice, we find situations where it is not possible to make any probability assessment. The EMV and preference criteria fail in such cases. The objective of this concluding section is to discuss some criteria that can be used under such circumstances. Criteria when probability is not known. Number 1. Criterion of pessimism. As the name suggests, the decision making is based on pessimism with the assumption that whatever alternative is chosen, the worst payoff corresponding to each alternative is actually going to occur. A rational criterion for decision making in such a case is to maximize the minimum payoff. Number 2. Criterion of optimism. A variant of criterion of pessimism, here over and above the maximum of the minimum payoff, say M1, the maximum of the maximum payoff, say M2, is determined. Choosing would mean complete optimism, that is the opposite of choosing MM. It is suggested that the DM find the maximum and minimum payoff for each alternative and then weigh them by his coefficient of optimism to arrive at the expected payoff for each alternative. The alternative with maximum expected payoff can then be chosen. Coefficient of optimism lies between 0 and 1. It gives us the degree by which the maximum payoff is favored by the DM vis-a-vis the minimum payoff. Number 3. Criterion of regret. The criteria stems from the fact that a regret inbuilt in the decision making as the final decision on an alternative and the actual outcome after the decision has been taken may not match. A regret of 0 occurs when it matches. Number 4. Subjectivist criterion. The outcomes are assumed to be equally probable in this case and EMV is used for decision. This is known as the subjectivist stand. The 4 mentioned criteria are the best known ones. Selection of the final criterion is purely subjective as the obvious by now. However, each provides us with a certain rationale and the DM can choose any depending on his own inclination. Now let's summarize the unit. Decision theory provides us with the framework and methods for analyzing decision problems under uncertainty. A decision problem under uncertainty is characterized by different alternative courses of action and uncertain outcomes corresponding to each action. The problems can involve a single stage or a multi-stage decision process. Marginal analysis is helpful in solving single-stage problems, whereas the decision tree approach is useful for solving multi-stage problems. In this unit, we have examined how these methods can be applied to solve decision problems. While using these methods, we have used the criterion of maximizing the expected monetary value or EMV. Thus, EMV basically assumes that the decision maker is risk neutral. Preference theory helps in incorporating the preference of the decision maker in the decision tree framework. We have understood how instead of maximizing the EMV, we can maximize the expected preference and thereby consider the decision maker's attitude towards risk. In the final section of this unit, we have examined certain other criteria that are helpful in taking decisions when the probabilities of occurrence of the outcomes are not known.
We were listening to the audiobook by the School of Management Studies IGNOU for MBA program, course code MMPC 005, Quantitative Analysis for Managerial Applications. Voiceover by Harpreet Kaur. Edited by Savita. Program assisted by Tarannum Jahan and Jagbandhu Jana. Program produced by Dr. Manoj Kumar Singh. This program was brought to you by Electronic Media Production Center of Indira Gandhi National Open University.